So let's look now at applications of periodic functions. And what we're really going to do is solve problems that involve trig functions. Now, the sine and cosine functions can be used to describe what's called periodic or harmonic motion. This type of motion that repeats over a fixed interval of time. And there's many examples of this, such as pendulums, springs, Ferris wheels, current, heartbeats, and a variety of others where this motion continues over a certain fixed time interval, and we get this same kind of motion. To solve questions that involve periodic motion, what we need to do is first determine the sinusoidal function, either sine or cos, that describes the motion. So we're trying to come up with a function, an equation. And the easiest way to do this is create a graph. Take the physical motion and transfer it to a graph. Let's look at an example of how we can do that. Typical example, Ferris wheel. The bottom of a Ferris wheel is 2 meters above the ground. The wheel rotates once every 20 seconds and it has a diameter of 12 meters. Brandon gets on the Ferris wheel at the bottom. Here's our motion, and we have a Ferris wheel, and we're going to try and transfer this data onto a graph. So the first thing we need to know is that the Ferris wheel is 2 meters above the ground. So down at its lowest point, it's 2 meters. The highest point, well, the highest point isn't given to us, but we're told that the diameter is 12 meters. Which means if it starts 2 meters down and a diameter of 12 meters, then up here we have a 14 meter maximum. Well, that's helpful because we can now transfer that to the graph. The minimum on our sine graph will be down here at 2, and a maximum will be up here at 14. Well, what else do we know? Well, we know this is a Ferris wheel, and we know there is some center to this Ferris wheel. And if the diameter is 12 meters, then we know the radius must be 6 meters. And it's 6 meters in each direction. Now that's helpful because from the radius, we go to our maximum and our minimum. The equivalent would be the midline on our sketch. The midline going from our middle point to a maximum and a minimum. Now, if the radius is 6, it's pretty easy to see here that our midline is at 8. So that information gives us the y coordinates of our sinusoidal function. Now let's think of the motion of this Ferris wheel. Brandon gets on the Ferris wheel down at the bottom. Now he'll be back at the bottom 20 seconds later. So he starts down at the bottom, and 20 seconds later he'll be back at the bottom. Well, that's going to help us establish the period. 20 seconds is our period, and Brandon is going to be back down at that lowest point. Well, if 20 seconds is one rotation, half a rotation would be 10 seconds. And that gives us our quarter intervals for our graph. Half is at 10 seconds. We follow the motion. At 10 seconds, Brandon's going to be up here at his maximum. And if we just think about this motion, a quarter turn when he gets to the 8 meter mark will occur at the 5 second mark, and back to that 8 meter at the 15 second mark. Now those points will allow us to graph this function. Now we may want to continue the pattern just so we have a better idea, and we'll just do this for 2 periods. The pattern just continues, and this will give us our sinusoidal function. Here is our graph. Nice smooth curve through those points, and we have this periodic or harmonic motion up and down of the Ferris wheel. So there's the graph. And from this graph, we can determine a lot of information, and we can also create an equation. So that's what we're going to do for part B. Determine the sine and cosine equations for the height as a function of time. So the height is this height up here in meters, and our time down here is in seconds. And we're going to try and create an equation in terms of sines and cosines that'll give us the height as a function of time. Well, let's first get the information from the graph that we need. Our amplitude. Amplitude in this case is just 6. The b value. Now the b value will come from the period. Remember, it's 2 pi divided by 20, which is then pi over 10 for the b value. What about our c value, our phase shift? Well, the phase shift is going to be different depending on sine and cosine, so we'll just ignore that for now. D, though, is the vertical shift, and remember the vertical shift is really just the same as the midline, which is just 8. So if we wanted to write an equation for the height as a function of time in terms of sine, well, the sine graph that we're going to concern ourselves with is we'll start right here and look at a sketch of this graph. There's the graph that has been translated. And that graph will give us the phase shift. So 6 is the amplitude, sine, our b value, pi over 10. Now our x in this case is t. And how has that sine graph been shifted? Well, it's been phase shifted 5 to the right. So we have minus 5 plus 8. There is the sine function in terms of h and t. And if we were given any time, we could plug that in and find the value of the height. Well, what about the cosine? The cosine function. And cosine function, we can choose to do positive or negative as well. I'm going to stick with the positive. So the first iteration of the cosine being positive is here, working its way to there. And again, when we do sine and cosine, not much changes. The amplitude is the same. Now we get cos. The b value is the same, pi over 10. T, the only thing that changes now is the phase shift. This graph has now been shifted over 10 units, in this case 10 seconds, and plus 8. There is the sine and cosine equations. Now there are others, but those would work, and those would allow us to find the height at any point in time. So that'll lead us to part C. Determine his height above the ground at 12 seconds. And once we have our sinusoidal equations, now we have choice. We want to determine the height at 12 seconds. We can use either one of these equations. I'm just going to choose sine to find the height when the time is 12 seconds. So we just take our equation exactly as we've created, and the t value that we're going to plug in is just 12. So we'll get 12 minus 5 plus 8. If we wanted to simplify that, we can. We'll get 6 sine. Now 12 minus 5 is 7, so we'll get 7 pi over 10 plus 8. But we have to be able to interpret this equation. We're not going to give the height in terms of sines and cosines. We want it in terms of meters. So we just fire it in our calculator. And you should get 12.8541. And if we want to do that to one decimal, we get a height of 12.9 meters. And once we have that sinusoidal function, we can find the height at any point in time. And we're going to continue to do application type problems in class, the whole key being take the word problem and create a picture.